Hello AP friends. Now we're going to start a new chapter today. In our Hunzoom class we talked already about slope fields, which is the beginning of chapter 7, but now we get to something a little bit meatier, and this is section 7.3. And it's basically what we're going to do is we're going to be taking more differential equations like dy dx or y prime, and we need to solve these differential equations, and our goal when we're done is to get y back out, get the original. We're given the derivatives, and your job is to go backwards and find this. And if we can just do the opposite, if we can just take the antiderivative or take the integral, that's great, and we would like that. But the problem is it's a lot more complicated now, and so we need to learn a new technique that we're going to call the separation of variables. So follow along, folks. All right, this is a really good worksheet that I'm going to put on RareNet for you folks a little bit later. But I'm going to start with some sample problems. So I'll give you a second to write down that title. This is not 5.2. In our book, it's 7.3. But it's called the separation of variables. And here's our goal, folks. Off to the side on the right, here's what we really want. You're given a very complicated equation, a differential equation. You need to solve for y. Your first goal is if you're given dy dx on one side, you want to make sure that you've got an equation on the right-hand side that has x on the top and an equation with y on the bottom. So basically, you want to have the same variables diagonal from each other. And we'll see in a second why that's really important. But that's your first big goal. Whatever differential equation you start with, try to get it into this form, where the same variables are diagonal from each other. So the y equation or y function should be on the bottom and the x function should be on top. So that means we might need to do a little bit of algebra magic before we start the problem, but that's our big goal and then we can go from there. Okay, let's try number 1. Now these questions are saying, can you find the general solution for each of the following differential equations? Which means we're going to try to solve for y. Can you get this all into y equals? All right, number 1, we have dy dx equals 2x over y. Now, like we said before, we have to make sure that the same variables are diagonal from each other. And right now it looks like it. The y and the dy are diagonal from each other, and the 2x and the dx are diagonal from each other. So we're good to go. We can totally proceed. But if it wasn't like that, we would have to mess with it a little bit and do a little bit of algebra to make sure it worked. But we're good to go. Okay, when you get it in that formation that we want, guys, the next step that you're going to do is you're going to cross multiply. The reason why, before I write that, the reason why we couldn't just take the integral, let's just take the antiderivative, the problem is you've got two variables on that side, and we can't take the antiderivative when you've got two variables. It just doesn't work. So you can only take the antiderivative or integrals when you've only got one variable on the inside. Okay, but like we said, we're good to go because we have the y is diagonal and the x is diagonal. So why don't we cross multiply and see what we get? That would be y times dy on one side equals 2x times dx. All right, so you get the variables diagonal from each other, and then we can cross multiply. Also notice after I do that, guys, is I have the same variables on both sides. I have the y's on the left side and I have all the x's on the right side. Now, I could do anything I want in math, and I could multiply both sides by 4. Don't write this down yet, but I can multiply that by 4, meaning if I multiply the right side by 4, I have to multiply the left side by 4. I could subtract 3 on the right side, so I have to subtract 3 on the left side. You know, math tells you that whatever you do to one side of an equation, you have to do to both. Well, if I have to do the same thing to both sides, here's what I'm going to do. Check this out. I'm going to take the integral, the antiderivative of both sides. That's legal because I am doing to both sides. Now look how cool this is. That means I've got an integral and I've already got my dy already there. So just by adding the integral, this actually looks like a regular indefinite integral. So by taking the integral on both sides, that's a big step too. You cross multiply, you got your same variables on the same sides, and then you integrate both sides. And now you can see the left integral will be in terms of y, so you'll solve that. And the right side will be an integral in terms of x. You'll solve that. And again, our goal is try to get y all by itself. All right, let's try it, guys. So let's take the integral of the left side. If I want to take the integral of y in terms of y, dy, well, by doing the reverse power rule, that would give me 1/2 y squared. And because this is an indefinite integral, we should have a plus c. And on the right side, let's do the same thing. Let's take the antiderivative of 2x dx. That should be x squared plus c. All right? But here's the thing, though. Are these c's the same number? Do we know? And we actually really don't, because when we take the antiderivative and you do the indefinite integral, they could be actually two different c's. So to be really picky, I should probably put c1 and c2. But do you see that in order to solve for y, do you see that I'm eventually going to have to move this c over anyway? I'm going to have to combine them and then maybe make like a new like c3 because he's a whole different c. It gets so complicated with these c's, guys. So can I give you a little bit of a shortcut? Let me go back for a second. When I took the antiderivative of the left side in terms of y, I'm not going to add a c. When I take the antiderivative of the right side, then I'm going to add my c. So there's really my first step. I took the antiderivative of the left side, don't put a c there. Take the antiderivative of the right side, then you can put your c. All right, so that's your c there. Now let's just start solving for y. So by doing some algebra, why don't we multiply everything by 2? Okay. Well, you know what? Interesting though, I'm going to really multiply this c by 2. It really should be 2c. But if c is a constant, do you guys agree that 2c is just going to give me another new constant? Maybe like a c1? So I can maybe plug that back in and just say, okay, this is 2x squared plus a new c. That would be fine. Or I can call this c1 from the beginning and call this c2. I will honestly say the only hard thing about these kind of equations is just keeping track of your c's. All right, so final answer. Let's take the square root of both sides. That means y is equal to square root of 2x squared plus c2. Now, because this is the only c left over, I can just leave it as a regular c because c is the constant. Now, I have to be a little careful though, folks. When I took the square root, I should get two answers. I get a plus or minus. Which one is it? I don't know. It could be either one. In a second, I'll show you how we can check and see which one is. So, we were given a differential equation. Our goal was to solve for y, and we did. That's the answer. That's the solution to our differential equation. Let's sum up. All right, first step. Again, you tried to get the x and the y's diagonal from each other. Once they were, you cross-multiplied. You took the integral or antiderivative of both sides. And then you took the antiderivative of both sides. And you got a constant, but you just kept it on the side with the c on the right. And then you just started to solve for y and get y all by itself. Don't let the c's throw you off. It's not a big deal. Some books will say, all right, this is 2x squared plus c2. And the AP exam will take that as well. That's fine. But can I show you why this is actually the answer? I'm going to go back a page for a second. Now, the original said dy dx is 2x over y. That was the beginning. Our solution was y equals plus or minus the square root of 2x squared plus c. That was our answer. Can we check why this actually works? Watch this. Let's actually check this answer by going backwards. Let's take the derivative of both sides. All right, y prime, which is the same thing as dy dx, is, ready? Let's take the derivative of the right side. Okay, if you want to think about this as really 2x squared plus c to the 1/2 power, here we go, ready? This becomes plus or minus 1/2 2x squared plus c to the negative 1/2 chain times 4x. So what's on the inside? Ready? dy dx. Let's just simplify. I see I've got that 1/2 here. I've got that 4x over here, so maybe I can simplify that to really just plus or minus 2x times 2x squared plus c to negative 1/2. You with me so far? Hey, that negative 1/2 power just means he can move downstairs because he's a negative exponent. So really, dy dx is plus or minus 2x over 2x squared plus c to the positive 1/2 now that he's downstairs. Okay, well, if I want to, I can be really picky and put the plus or minus on the bottom. I'll show you in a second why the heck am I doing that. And then remember, what's the 1/2 power? That's the square root of 2x squared plus c. So really, dy dx is 2x over plus or minus the square root of 2x squared plus c. Now, take a breather. Does that denominator look kind of familiar to you at all? Have we seen that somewhere before? That's y, right? So if this is equal to y, ready? The derivative dy dx is equal to 2x over y, right? Because y was our solution that we actually found. I just subbed it back in. Hey, what was the original question? Oh, look, we just proved it. So a way to double check your answer with differential equations is to now take the derivative and see if you get the original back out. So the answer to the first one is plus or minus the square root of 2x squared plus a constant c. Okay, let's try number 2 together, or b. All right, for b, we need to find now what's the original y equals. If I'm giving dy dx, the differential equation equals y squared. Again, our goal, like we set up here, is I need to get the x's diagonal from each other and the y's diagonal from each other. Now, there are no x's here, there's only y's. And if dy is on the top, I need this y to somehow be on the bottom. This is where your algebra skills need to be good. Well, how can I get that y squared to be on the bottom? Well, if I move it downstairs, I'm just going to have to change its exponent, right? So what if I move it downstairs and call it this? Do you agree that that's the same thing as this? So now dy is on the top left and the y function is on the bottom right. They match. Now notice that the dx and the 1, I mean there's no x here on the 1, but we can still pair them together because it's not a y. So that's it. That's a first big step, guys. A little bit of algebra magic here. Dy dx equals 1 over y to the negative 2 power. Okay, we're set to continue. But that's the first big step. Ready? Y's are diagonal, x's are diagonal. Let's cross multiply. And we get y to the negative 2 dy equals 1 dx. Okay, y's are on one side, x's are on the other. We're good to go. Let's take the integral of both sides and take the antiderivative. All right, now the antiderivative y to the negative 2, it's a little bit ugly, but we get negative y to the negative 1 equals, notice I'm going to put the constant on the right side. Well, the antiderivative of 1 is just regular x. And then there's my plus c. All right, I'll call this, just for the heck of it, let's see what happens if I keep track of all my constants this time. I'll call that c1. All right, now we need to get y all by itself. There's a couple things going on. We have that negative in the front and the negative power. I'm going to deal with the negative in the front first. So we multiply everything through by negative 1. So y to the negative 1 is equal to negative x minus c1. Okay, well that minus c1, if I multiply negative to a c, I would just change it to another constant. So a negative c1 just becomes a brand new constant. I'll call it c2. So really, y to negative 1 equals negative x plus a new constant, c2. All right, now we need to get that y by itself. Remember, y to the negative 1 is really just 1 over y. So if I want to solve that for y, best thing to do is just to flip it over and make it y over 1. So in order to do that, if I flip the left side, I got to flip that right side. So that means over here, y over 1, or just y. If I flip the left side, let's flip the right side. If I flip the left, let's flip the right. This becomes 1 over negative x plus c2. All right, we did it. That's the answer. I solved for y and we're good to go. Now, do you want to just leave that as just a normal c and not c2? That's also fine. Again, the AP doesn't really keep track that much, so it's okay. There's your answer. That's the answer to the differential equation of part B. dy dx equals y squared. All right, I'm going to work through, in a new video, I'm going to work through C and D with you together. But if you want to go ahead and try C and D right now, and then you can start the next video and check your answers. See you soon.